Welcome to lesson 2 of module 3 scientific models. And in this video, we're going to be looking at what makes scientific models useful and when should a particular model be used. So the first thing I want you to do is to watch this video that's hyperlinked in the Google slide, and I want you to identify the main points in the think, pair, share activity. So make sure you pause this video, play this video that is linked in here, and then complete that activity. So you can do that now. So in terms of our syllabus requirements for this lesson, we're going to start looking at epidemic models, models of the universe, atomic models, and climate models. And we're going to be looking at how they are used and also why new evidence challenges the models that were originally proposed for those ideas and how they've been replaced or refined over time. So when we use models, they're for a variety of reasons, and we're using the VESP acronym here. So models are used to visualize, explain, simplify, and predict. So what I'm going to get you to do now is pause the video and complete the fill in the blanks activity in your Google Doc. The first type of models we're going to look at are epidemic models. And an epidemic is when a disease quickly spreads through a population. And the most commonly accepted model for that is the germ theory of disease. And this theory states that infectious diseases are spread by germs. In this context, germs are referred to as anything that can pass from one organism to another, and pathogens are referred to as disease causing organisms. And this germ theory has been very successful in explaining the cause and spread of epidemics. And I have a little advertisement here from the time of the influenza, and we can see here how they've tried to use that germ theory in a public health campaign about way to keep people safe from influenza and other serious diseases. So, in terms of the different theories that happened over time, the first was the Hippocratic corpus. And this was the idea that the sickness was an imbalance of the humours, melancholy, phlegm, bile, and blood of the body. And it was similar to the ancient Chinese, where there was an imbalance between the yin and the yang. So, that was the first idea. The next came the miasma theory. And this was the idea that sickness was spread by bad or foul air. And this, in fact, did have some truth due to the lack of the sanitary conditions at the time. The first kind of closest idea to what we have now was developed in the 1500s. And Fracastro had the idea that sickness was spread by tiny particles or spores in the air by direct or indirect contact. And it wasn't until the development of the microscope, where Leeuwenhoek was the first person to observe single celled organisms, where the idea started to really shift into the germ theory that we have today. So, the activities regarding to epidemic models is I want you to um, play the simulation and then complete the table that deconstructs the simulation. So this is here how we're looking at how an infectious disease can be passed through a population using a simulation, so a computer simulation that we looked at in lesson 1. And the next is there's two experiments. The first is modeling diseases, so that's a card game. And then the second, which you'll find in your Google Doc, is disease detectives with phenolphthalein, which is through contact tracing, which is in fact what they're doing with COVID-19 currently. So it's got to do with this idea, and the image there relates to what that experiment might look like when we're performing it in classroom. The next are models of the universe, and there have been many ideas put forward to explain how the stars, the sun, and the moon move in relation to the Earth. And the two ideas which we're seeing on this slide here are the geocentric theory and the heliocentric theory. And the heliocentric theory is the theory that still exists today. So the geocentric idea um, was that the Earth was the center of everything, and it was proposed in 400 BCE. And it wasn't until Galileo observed stars that he thought that the sun was the center of the universe. And then indeed shifted from the geocentric model that we were looking at previously. There's the idea of how the universe was created, and I guess there's steady state, which is the idea here that the universe had always existed and nothing changed over time, which you can see in the bottom diagram in the picture to the right. And then there's the Big Bang, where the entire universe existed in one tiny region, then rapidly expanded and this is evidenced by the Doppler effect. And indeed, we see the evidence here in the redshift, so that spectral lines are observed in the light that's coming from distant celestial objects. And this was also observed when Hubble discovered that the redshift indicated that these objects were actually, in fact, moving away from each other. And this led to the idea that they were obviously much closer in previous times, and the universe at one point was a singularity. And this is the model that we still use for the universe today. So, two activities to look at models of the universe. So, there's the research table using the links to look at the changing theories of the universe. And then there's some questions that follow those. And the second is the investigation with the expanding balloon universe. So, following the instructions in your Google Doc to perform that investigation. The next are atomic models, and relating to the idea that all matter in the universe is made of atoms. And the most current model of the atom is known as the quantum mechanical model. And in this model, the atom has a dense nucleus made of protons and neutrons, where electrons are orbiting the nucleus, and there's a lot of space, as we can see in the picture, between the two regions there. And in the quantum mechanical model is where we have the idea of the orbitals. So, this is a quick summary of the history of the atom and how the theory changed over time, starting with John Dalton with the solid sphere model, then to the plum pudding model proposed by J.J. Thomson, the nuclear model by Rutherford, then we have the planetary model proposed by Niels Bohr, and we have the quantum model by Schrödinger as early as late, sorry, as 1926. So, you can use this for some of your research activities. So the two activities I want you to investigate is to complete the simulation of building an atom using the PhET simulator, and then watching the YouTube video that is about the atomic theory and how it's changed over time. And then there's several questions that follow that. And then the final investigation for the atomic model is to complete the investigation with molecular model kits. And finally, we have climate models. And from the 1950s, the use of the computer modeling was allowed scientists to predict what might happen if greenhouse gases were emitted into the atmosphere. And so these predictions in the model actually mimic the measured data that we've been collecting over time. And the large and complex computer algorithms, in fact, may prove less accurate over longer time periods as more data is collected. So, can you pause the video now and watch this video from the CSIRO about how they use climate modeling? And then the activities related to climate modeling. So, if you follow the links on your Google Doc, there's a climate model simulation, and there's a series of questions that follow that simulation about how the carbon dioxide emissions change over time. And then there's a reading, which we're going to do rigorous reading on about climate models. So using the annotation symbols and the literal and inferential questions that follow are also on your Google Doc. This has been a very long lesson, lesson two, but the last activity we need to do is to update our inquiry question log. And this lesson had two inquiry questions that we were looking at. So, what makes scientific models useful? And when should a particular model be used?